Hello, welcome back to the low power VLSI lecture. Today we'll start with chapter 3. In this lecture, we'll discuss about introduction to the sources of power dissipation. Third chapter title is sources of power dissipation, and introduction will be given in this lecture. Now, the power dissipation may be specified in two ways. Chapter title is sources of power dissipation. Now here we are talking about the same sources of power dissipation. Power dissipation may be specified in two ways. One is maximum power dissipation, other one is average power dissipation. As these two names differ and the names itself is suggesting maximum power dissipation means the instantaneous power that is being consumed right now. Consider, for example, half of a sine wave, half wave of a sine, that is at 90 degrees. What will be the sine wave situation? It is at the peak, right? So that's how. So the maximum power dissipation is the instantaneous power dissipation that occurs when the circuit draws maximum power. When the circuit draws maximum power, that is called as maximum power dissipation. Coming to the average power dissipation, both are completely different. If the peak power is drawn all the times, then the average power dissipation will be high, because average power dissipation is defined as the power dissipated over a period of time, right? So when a peak power is dissipated all the times, what will be the average? Average will go high. Now, if sometimes high, sometimes low, sometimes very less power consumption is happening, then the average power will be moderate. So for the battery operated devices like portable devices like laptops, mobiles and all, this average power dissipation is concentrated much. It should be less. If this is not less, the battery will drain very soon, which is not suitable for the portable devices. So there are two different kinds of things that we have to understand at this point of time. Power consumption is different, energy consumption is different. The curve consider a curve. I will try to draw. If this is time and this is power, y-axis, this is the maximum power that is consumed, and the energy is area under this curve gives you power. So if you integrate this curve p of t from 0 to t, then the integral gives you, then that integral gives you energy of the signal. So power is different and energy is different. Energy is area under the curve. So that is the reason why all our batteries and battery operated devices have the batteries rated as milliamp hours, 6000 milliamp hours, 5000 milliamp hours. That is, for portable devices the power consumption is treated as energy consumption and it is rated in milliamp hours, because we always have bothering about the energy consumption, not the power all the times. So with this introduction, let us jump into these types of power dissipation. Types of power dissipation is of two types. One is static power dissipation and the another one is dynamic power dissipation. What is static power dissipation? If the inputs and outputs are not changing, then it is called as static power dissipation. Or the other way of representing this is both pull up and pull down devices are simultaneously on for a very low output levels, causing direct current flow. Both devices, pull up and pull down devices, are on during some particular time. That means no change, but both the devices are on. That time the power is consumed is called as static power dissipation. Whereas the dynamic power dissipation is due to the changing levels of input and output is called as dynamic power dissipation. When the circuit is active and the circuit is working, inputs and outputs keeps changing. Whenever load capacitor charges and discharges slowly, it incurs power dissipation. Whenever a input signal or the output signal changes its level, the time required to change its level will be very short. The power consumed during that short period, the period which takes for a signal from shifting from 0 to 1 going up, that short time, whatever the power consumed, that is called as dynamic power dissipation. The mechanisms, see here at this point I wanted to tell one thing, that if you want to reduce the power consumption, you have to change the design of your system. To reduce the energy, you can change. For example, if your clock speed is 1 gigahertz and it is consuming some X amount of energy, you can reduce the energy consumption by making the clock frequency half. If you make the clock frequency half, your energy consumed will be half. At the same time, the number of operations that take place for every second will also be half. That means the processor takes 2 seconds of time, whereas previously it was 1 second. Now it will take 2 seconds of time and execute the instruction. Now what happened? Energy consumed has become half. Time of execution have doubled. Now the overall energy consumption for each given set of tasks is same. What has differed here? The difference here is the average power consumption has gone down. Half of the energy means half of the power being consumed for each at any point of time. What is the advantage means? When the average power consumption goes down, circuit does not get heated up very quickly, and it will be protected. Otherwise, circuit may malfunction or may damage. It cannot be protected. Cooling mechanisms fails and the device also fails. There is a tendency of device failure also. Okay, come back this mechanisms involved in dynamic power dissipation. There are 3 types of dynamic power dissipations may take place. One is short circuit power dissipation, switching power dissipation, and glitching power dissipation. Short circuit power dissipation occurs when both NMOS and PMOS networks are on. That means consider a CMOS inverter whose drain is connected, pull up device drain is connected to supply and pull down device source is connected to ground. What if both the devices are on? If both the devices are on, the supply current flows from the pull up device through pull down device also and reaches the ground. This is called as short circuit power dissipation. Understood? And the main reason for this short circuit power dissipation is slow rise and fall times of inputs. If the input is slowly rising for a very short period of time, when V in is 0.5 VDD, which is equal to VINV. If that is equal to VINV, that time both the devices will be in saturation. Then the direct current flows from supply to ground. That is short circuit power dissipation. Next is switching power dissipation. As the input and output values keeps on changing, the capacitive load at different circuit points are charged and discharged. These chargings and dischargings lead to a power dissipation which is called as switching power dissipation. This is called switching power dissipation because this dissipation is happening because of the switching activity that is taking place because of the change in the input. Okay, now the third type of power dissipation is a glitching power dissipation. This glitch power dissipation happens because of the finite delays in the logic circuits. For example, if one input is directly connected to the third stage, another input is connected to the first stage, which has to pass stage 1 and stage 2 and has to come to the third stage. Consider another input which is connected to the second stage, that has to pass only one stage and come to the output. Here in the three inputs to the third stage, one is directly connected, another one is through one network, and third one is connected to through two networks. Now the propagation delay that has happened because of the one network comes faster. The first direct input comes first. Second input will be the signal which is coming through the one network is coming second, and after some delay the signal which is coming through passing through two networks will be coming. Now these three inputs arrived at the third stage at three different times. Now because of this finite delay, a switching activity takes place. Unnecessary switching activity takes place at the output of third stage. Because of this unnecessary switching activity, as just now we have seen, switching power dissipation takes place. That switching power dissipation that has happened because of the finite delay of the logic gates is called as glitching power dissipation. This is the all these are short circuit switching power and glitching power dissipations are dynamic power dissipations, whereas this is the static power dissipation. The static power dissipation is because of these leakage currents that are happening. 7 different kinds of leakage currents may take place in a MOS transistor. Because of these 7 kind of continuous current leakages, the power is being consumed. That power is called as static power dissipation. The first one is reverse bias PN junction diode leakage current, because consider if this substrate is of P substrate, and definitely these diffusions, source and drain, will be of N type. N type and P type together is a junction, PN junction. The PN junction, this is connected to, for example, if this is connected to a positive supply, which is N type. N type is connected to positive supply and P type is connected to ground, which is nothing but reverse bias. Every reverse bias diode will have some leakage current. That current is called as reverse bias PN junction leakage current. Got my point? Second one is here I1 and I2, both currents are reverse bias leakage currents. Reverse bias, the second current is reverse bias PN junction current due to the tunneling of electrons from valence band to the conduction band of the region. Some electrons which are there in the conduction valence band may be attracted to the valence band because of the heat, because of the light, maybe because of the electric field, or because of the rupture of the rupture due to other electrons. All these currents are treated as I2, reverse bias PN junction current due to the tunneling of electrons from conduction band to valence band. The next one is subthreshold leakage current between the source and drain when the gate voltage is less than the threshold voltage Vt. Whenever the gate voltage is less than Vt, we consider gate not formed. We know that gate will not form before when the gate voltage is less than Vt. Even then, some charge carriers are coming from drain to source. That current is called as subthreshold, less than the threshold, subthreshold, less than the threshold. current that is flowing is called as subserial leakage current between source and drain. Next is oxide tunneling. See, when the device is scaled down along with drain size, source size, substrate size, gate size, the thickness of SiO2 or the gate dielectric will also gets reduced. Because of the reduced oxide thickness, some charge carriers will forcibly pass through the insulating material because of the high field. This type of unintended charge carrier flow through the oxide layer is called as oxide tunneling current. The next current is hot current, gate current due to hot carrier injection of electrons. This hot carrier injection is also similar to the tunneling current, but it is because of the, as just now we have seen, the charge carriers which are changing from valence band to conduction band. These electrons are tunneling. So that type of tunneling is called as the hot carrier injection tunneling. Gate induced drain leakage current. The drain, see here, if you can see, some part of the drain overlaps the comes under the gate structure. Because gate is applied with high potential, sometimes this gate influences a little current induction in the drain. That is called as gate induced drain leakage current. The last one is channel punch through. All the charge carriers are expected to travel through the channel, but some charge carriers does not take the path of the channel. They take directly, they don't travel through the channel, but they travel through the substrate and DC. That is called as channel punch through. So these are the different kinds of static and dynamic power leakage, power dissipation mechanisms, which can be considered as the introduction of sources of power dissipation. I hope you understood the topic. Thank you.